All right, well, welcome back, everybody. So here for lecture 2 of dens and nests and cat animals and cubs, and take it away.
All right, thank you. So just a recap, last time we were giving a background talk on like how things are related with geometry, algebra, and combinatorics. And then afterwards, we're saying that, okay, well, we have a way to generalize like the Warrington conjecture in an MN way if we use the cat and animal, our cat. And then if we choose our MN, so each universe that you choose in the, like we call it the elliptical algebra or Schiffman algebra, just take the copy that you like. Each copy gives you some element here. So that is how we generalize to an MN version. And on the left-hand side, you have some geometric meaning and also algebraical meaning. But like the whole point is like, can you find a combinatorial meaning? And then, so last time, towards the end of the talk, we talk about, hey, yeah, they actually have something like this. And I briefly explained that how you can get that. So just like a frame of the proof. So for today, my goal is to just, because Teddy also asked me to like, is there any like easy example, right? So because of all these statistics, there's a little bit complicated. So my goal is to go through all these statistics with you one by one with specific example to tell you, okay, well, choose your MN, choose your lambda. What is the combinatorial formula on the right-hand side? How am I going to compute them? And then I will tell you what is next. And then in this very specific situation, and hopefully next lecture, then I can give you a more generalized version of the dens and nest, and then tell you why they are important in the cat and animal that we are looking at. So that's our goal. So to just give you the full theorem, here is the sure. If you choose the MN equals to 1, then you get back the nabla of sure functions. And if you just pick n equals 1, then it's this nabla applied to m times on the sure functions. And that's the right-hand side that we have. So let's get started and see what all these things means. So the first guy is the p lambda. So what is p lambda here? So p lambda is just the number of boxes in lambda with positive content. Here, content means the column minus row. Okay. So in our project, we use the French notation. Sorry for like the first talk, I used the English notation. This one is the French notation. Basically, I am having the row upside down. So the longest row will be at the bottom. And so that's like our lambda 433. And then so like column minus row. So how do you count that? Very easy. You just draw the diagonal and then count the complete boxes on the right. For example, this guy, the column is 2 and the row is 1. So 2 minus 1 is 1, is this positive, right? And say, for example, you choose this one. Sorry. Let me go back. Yeah, so if you choose this one, then the column is 1, but the row is 3. So 1 minus 3 is -2. So you have a negative content. So here is to distinguish the content from negative and positive. Everything on this diagonal would have content 0. So that's how you compute the p lambda. Very easy. Just draw the diagonal, count the number of complete boxes on the right. So in this case, if I just have this, then my p lambda is just 4, so 4 boxes. So that's what this p lambda means. All right, so just to give you an idea, m and n are fixed. So you choose your m and n, okay? So m and n is like the label of the universe that you like. And then now with this h here, this h is m times the largest hook length in lambda. So for example, our running example is this 433, draw the longest hook, and your longest hooks have 1, 2, 3, 4, 5, 6. So there's 6 boxes. So if I choose any m, then h would be 6 times m. So if you choose m to be 2, then that would be 12. If you choose m to be 3, then h would be 18. So that's how we define the h. Now, what is this gamma I? So this gamma I, it's just the number.
Just reference. This longest, largest hook sometimes or recently is being called the perimeter of partition.
Okay. Thank you for the notes. I learned something. So this gamma I is just the number of boxes in the ith diagonal of lambda, and we order the diagonal from the smallest content. So it's from the kind of the left northwest corner to the southeast corner. So let's start with an example. So how do we find all these like gamma I? So this is the first gamma. So that's the smallest content, and I have only one box, so that's 1 here. And I have 2 boxes, and I have 3 boxes, and I have 2 boxes and 1 box and 1 box. So that's 1, 2, 3, 2, 1, 1. So you read like this. And then to compute the summation, you just add them up. So 1 choose 2, 2 choose 2, 3 choose 2, and so on. So a bunch of them are zeros, and then this is 1 plus 3 plus 1, so you get the 5. So that's the 5 here, and then you times the n. So that gives you the QT power here.
Anna, you can call that to the X-ray of a partition.
Okay, thank you. So, and then, okay, so what is this small p? This p is not the same as this p here. This p is kind of like a function, and this is like a fixed number. So this fixed number is that it's n minus n over m. So you choose your n and m, and then you minus a very small epsilon. So this small epsilon, so that like to guarantee that this p is not a rational function, with rational number. So that's the p here. And then now, what is this like? Loehr Warrington. So LW is Loehr Warrington then for lambda and mn. So you choose your lambda, choose your mn. I'm going to give you a then. To construct the then, there are some notations that we have to talk about first. So the first notation is the delta I of lambda. And this chi is just like the statement is true, then it's 1, the statement is not true, then it's 0. So it is just saying that like, if this is the content of the last part of some row of lambda. So it looks very complicated. So let's start with example. Okay, so we have 433. All right. So what you do is that because it says that the content of the last box, right? So you just write down the content of the last box of each row. All right. And so the content of the last box of each row is 0, 1, and 3. So what is this like delta lambda? So I claim that is this 1, 0, 1, 1, and then 0 afterwards. Why? Okay, so, and we order I starting from 0. Okay, so let's check. So when I is 0, so lambda I minus 1 minus 0 is 4 minus 1, so it's 3. 3 minus 0 is 3. So 3 is here. So that's why I have a 1. And then when my I is 1, then 4 minus 1 is 2. 2 is not here. So that's why I have a 0. So that now you should be able to find it very easily, because this gives you a 3, this gives you a 2, this gives you a 1, and 1 is here. This gives you a 0, 0 is here. And then this gives you a minus 1, minus 2, minus 3, and so on. So all these are minus sign, and there's no minus signs here. So that's why all zeros. So that's how you compute this like delta I. And then another thing called epsilon I lambda. It's just basically saying that if my I is bigger than lambda 1. So in this case, it's very easy. Again, you start with I equal to 0. So 0 is not bigger than 4. So 0 is not, 1 is not, 2 is not, 3 is not, and then 4 afterwards, that's all ones. So this is our delta and the epsilon. These two sequences is going to help us to build a then. All right. All right. So we have that here. So how do we construct something called Loehr Warrington then? So again, to make sure you realize that that's a simplified version that I simplified it for you. Next time we are going to go through a more complicated version. So, okay, so first of all, you draw the line connecting 0 to nh over m and h0. Okay, I'm going to give you an example. And so what it is that this line has this slope, minus n over m. And then if the two sequences have the same entry 0, then you plot the highest lattice point strictly below the line x equals mi. Otherwise, you pick the highest lattice points weakly below. Okay, so the difference is that if they are both 0, take the highest lattice point strictly below. Otherwise, you take the highest lattice point weakly below the line. So let's see. So we have this, right? We have this thing. We already calculated h, delta, and epsilon. And say I pick m equals 3 and n equals 2. All right. So now we draw this line. So let's see, draw the line 2/3 times 18. So it's 12. So 0, 12. And then on the x-axis here is 18, 0. So that is the line here. Okay, so if these sequence, both of them are 0, so let's see, these two are 0, then this is when I equals 1. My m is 3, so on the 3 here, I'm going to find the highest lattice point strictly below the line. So you can see that this point is also a lattice point, but it is not strictly below, so I choose this one. And there's no other point, right? Like there's no other both 0, so that is the only point that we plot. Otherwise, we are going to plot the highest lattice point weakly below the line. So you can see that some of them lies on the line, some of them are not, but it's the highest lattice point that you can find. So that's that. So that's how you draw this. Okay. And this guy is already called a dent. So that's how you construct a dent. Very easy. Pick your m and n, pick your lambda, compute your delta and epsilon, and then these, like the second step is just like you find the forbidden lattice point, something like that. And then afterwards, you just find the highest lattice point weakly below your line. That gives you a dent. All right. And then, so we call some, like, after you give me a dent, I'm going to name some of the points. So if my delta I is bigger than epsilon I, we call the lattice point a source. So these 3 purple ones are the source, okay? And if the other way around, then we call it a sink. So these 3 here are like these 3, okay? So these 3 guys are the sink. So I know that there are more here, but we only care about this line. Okay, so we don't care about things below the x-axis. So we only have this. Now, then we order the source from the left to right, and then order the sinks from right to left. You can actually easily prove that the number of sources and the number of sinks are the same. Okay, so that's that. So you can see that my purple one is 1, 2, 3 like this, and the yellow one is 1, 2, 3 like this. And the construction actually guarantees that all the sources would be on the left of all the sinks. So you can just have like 1, 2, 3, 4, 5 like that. Okay. All right. So that is what it means by the LW then. All right. And then what is a nest? So give you some notations. First of all, I'm going to talk about a lot of something called an east end path. That just means that a lattice path that ends with an east end. And then if you give me an east end, 2 east end path pi and pi prime, what it means by like they are nested, like one is nested below the other one, is that if the range of the x-axis of the pi prime is contained in the range of the x coordinates of pi prime is contained in the range of the x coordinates of pi, what it means is that looking at the starting point and the ending point of the pi, and then looking at that for pi prime is strictly inside those in pi. So I'm going to give you examples to make it more clear later. Okay, and the next condition that you have to satisfy is that the top of the self-run of pi prime is strictly above the top of the self-run of pi, of course, because you want to say that pi is lower, so pi prime is higher, so everything is higher. And same for the bottom part of the self-run. So that just means that pi prime has to be something like this. You can have something like that as well. But make sure that pi prime, every line, the starting and the ending point is strictly above the ones in pi if they are on the same x coordinate line. So a nest, by definition, is just a system of nested paths, nested each-end path, staying below the line that we drew. And then starting at, and pi I means that it starts from the I source and then ends in at the I sink, and that's it. So there are lots of notations here. So we are going to build a nest together, okay? So we have this then. And how are we going to build a nest? So you start from the highest number, so 3 and 3. So your goal is to draw a path going south or east. Make sure the last step is east, and then start from 3 and ends at 3. There are not many choices here, right? Because if you already have 1 line here, then you only have this choice or that choice. So there are only 2 choices for pi 3. So for me, I'm just going to just draw 1. Okay, so that's 1 line. Okay, now I'm going to draw another line from another path from 2 to 2. So I'm going to connect from 2 to 2. But I want to satisfy all the conditions here. So I just like draw the highest point that I can do. Okay, so let's see, are they nested? Well, first of all, you can see that 2 and 2, it starts from here, ends at here, right? And then the 3 is starting on the right of 2, ending on the left of the end of 2. So the x coordinates of the blue path is contained in the x coordinates of the green path. So that is what it means by the first condition. Okay. Second condition, and look at each vertical line. Okay, so see if there are 2 different colors on the same, with the same x coordinate. So here it is, right? And then you see that, well, the blue line, the starting point of the blue line and the starting point of the green is like the blue one is higher than the green. Same for the ending point, then you are safe. So this one for this 2 is the same, like this is higher than this. So that is nested. So satisfy 1, 2, and 3. So that's good. These 2 guys are nested. And then you can do the same thing for the 1. And so, and if you kind of pay attention, you will realize that like I'm drawing the highest possible lattice path every single time, starting from the 3, right? So because they are the highest one, I have like a special notation for the knot to say that, okay, well, that's the highest one. Okay, so that's our notation. And we'll use that later. And give you another example. So you can actually draw another pi 3 like this. And then I can draw a 2 like this. Now you can see that like they actually overlap, but it is fine because the whole vertical line here, it starts here. The green one starts here. So as long as the starting point, the blue one is higher, strictly higher than the green one, and the ending point is strictly higher than the green one, then it is still nested. Okay, so this is good. And this is like, you can draw more. You don't have to find the highest lattice path. As long as you're a southeast path with ending with an east step, which you should, because otherwise you're going from the top, which will be crossing this pink line. And so you should be able to draw all these east-end paths and then connecting the numbers, and then make sure they are nested, and that's it. So that's another nest. So given a then, you can actually draw a bunch of nests. So there are lots of nests there. Okay, so that's the nest. So hopefully now you understand that I give you an mn, give you a lambda, you can make your den, and then after you have a den, you can build your nest in a way that you like. And then now the next thing is that, okay, I build my nest now. What is the meaning of an area? So the area is actually relying on the highest lattice path that we can draw. So what it means is that you are trying to find the number of complete lattice square between pi I and pi I naught. So let's start with an example. We drew these two nests, right? This is the highest one with the knot on the top. And then, so what you do is that you compare each of them. So pi 3 naught and pi 3, you compare. And pi 2 naught and pi 2 you compare, pi 1 and pi 1 naught you compare. So say, for example, I'll compare pi 1 naught here, okay? And then see how many complete squares. So there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, and 15. So there are 15 complete squares. So that's why the area is 15. And then you do everything with the pi 2 naught and pi 2, pi 3 naught and pi 3. Then you have all this area for each of the pi I, and then you add them up. So that is what it means by this area. All right. Now the dimph. Okay. So the dimph is a little bit complicated. It's just counting this tuple, PISJ. Okay, so what are these? P is a non-sync lattice point in pi I. So that's P in pi I, but non-sync. S is a self-step in pi J. So S and J related. And we want P is strictly left of S. And the line passing the line of slope minus P, just to recall what is minus P, P is N over M minus an epsilon to make sure it's a irrational number. So that is kind of like you shift the slope a little bit. And then make sure that that line passing through P also pass through S. So what's going on? Basically, I want this configuration. I want a lattice point, make sure it's non-sync, and then I want a self-step, and then draw a line through P with the slope minus this P. And the good thing about P is irrational is that I will cut the self-step internally. I don't have to worry about it cuts the top or the bottom. So then I want to find how many configurations like this in our nest. So that can be complicated. Okay, so let's look at this nest, okay? And then we pick a point. Okay, so that's our P. So make sure it's non-sync. Non-sync means that it's not this yellow dot. Okay, and then this P is on pi 1 and on pi 2. Okay, so your I can be 1 or 2. And then how are you going to count this configuration? So you tilt the line a little bit, so that becomes the other line here, the yellow line, and you just shift so that you pass through P. And now you count how many self lines like that you are cutting. So you are cutting all these. So the red one, see, 1, and then you cut the green one and the blue one. You cut the green one and also this one. So you cut 1, 2, 3, 4, 5. You cut 5 of them. So there are 5 SJ pair with your chosen P, and each of them, each P is lying on I equals 1 or 2. So just looking at this P, you're giving like 5 times 2, which is 10 contribution to this dimph pi. So what you need to do is to just like going through all these like lattice paths, choose a lattice point on them, and then do this step one by one, and then add them up. So that gives you the dimph P pi. Okay, so yeah, it's not easy to calculate, but it works. All right. So the remaining thing that I have to tell you is that, okay, well, we know all the statistics now. Now the only issue is that we want to write this thing in terms of LLT polynomials. And what are the associated LLT polynomial if I give you a nest? So that's the new pi that I'm writing here. If I know this, then the whole theorem on the right-hand side should be clear. Okay. So new pi is constructed in this way. So first of all, you choose your S such that the line y equals minus px plus s is weakly above all the points in your den. And then each x equals I correspond to a skew tableau. So because our x-axis, if you remember, we draw this graph is from like the x coordinate is h0. So that's why there are h skew shape. And then the number of rows in the skew tableau is the same as the number of paths passing through x equals I. Number of boxes in row J is the number of cell steps in pi j on x equals I. And this is starting from the bottom. And then the property is that there are empty boxes on the left of row J. And what is this R? R is the J plus the distance between the highest lattice point below the path that you drew and the highest lattice point on pi j on x equals I. Okay, I know there are lots of like words here, so don't worry. As usual, I'm going to give you like an example, but just give you an idea. Like, okay, you choose your S, and then make sure that your line is like weakly above all the points on your den. Satisfying. Then we are going to construct tableaus using these conditions. Now, you will construct a lot of tableaus because there are each of them, right? And then how are you going to order them? So to order these tableaus, you have to compare the distance between the highest lattice point and the path that you drew. And then we order the tableau according to the value of CI strictly increasingly. And why is it strictly? Because your line is having a irrational slope. So there's no hope that there would be two distances that would be the same. Anyway, so this is our one of the nest. How are you going to associate some tableau to it, right? So first of all, let me just do this. So oops, sorry about like, hey, bad thing about animation. Sorry about that. All right, so this is the pink line is the one that we usually drew, and then the yellow line is the one that we shifted, and then last time we shift to P to find the dim. So it's using the same slope because it's minus P, right? But now I have to shift it a little bit higher because there are some points that are may not be weakly, may not be all below me. So I have to shift it a little bit to make sure that every single point here is below my yellow line. So, and then my S is just a y-intercept here, okay? So the S is not that important. The important thing is that you shift it in the right parallel line, okay? All right, so now, how am I going to draw our tableau? So this guy is S. So say, for example, I choose I equals 9, okay? Because each x equals I corresponds to a skew tableau. So I choose I equals 9 here. I want to draw some tableau. How am I going to do that? So first of all, you go up, and then the pi I has one cell front. So you have one box, okay? The pi 2 has two cell fronts, so you have two boxes. And then the pi 3 has two boxes again, all right? So that is what it means by the number of boxes in row J, row 1, row 2, and row 3, is the number of cell steps in pi j, okay? So pi 1, pi 2, pi 3, when on the I that you chose. So that is what it means. Now, I have to shift it because it's a skew tableau. I have to know how much I'll shift it. So the shift is just shifting J plus the distance between the highest lattice point below the yellow line. So here, this is the highest lattice point, right? So from the top of me, like this vertical line, I have 1, 2, 3, 4. So you have 1 plus 4. Why is that 1? Because you're from pi 1, okay? 1 plus 4. So that's why there are 5 boxes that you shift to the right. So look at 2. The distance is 1. and your index is 2. So 2 plus 1 is 3. So you shift by 3. And then pi 3, there's no distance here. So distance is 0, but your index j is 3. So 3 plus 0 is 3. So that's how you shift them. Okay, so that's what it means here. Now you put them together. That is the skew tableau corresponding to this vertical line. So each vertical line, you can draw skew tableau. Some of them may be empty tableau, okay, but no box, because there's no self-run. All right. So now I have this I equals 9. And for LFT polynomial, there are like tableaus lying up on the diagonal. So you have to know this tableau that I construct, where am I going to put it? So I put it at the lowest one, the middle one, the highest one, which one, right? So to order them, what you do is that you compare the highest lattice point. So you have this yellow line that we drew, and then you have all these like highest lattice point, right? And this is our highest lattice point when I equals 9. And you look at all the distance, okay? And then because this line is irrational, so none of them would be equal to another one, okay? So you can order them in a strictly increasing order. So say, for example, this guy is maybe the third smallest one, then this is the third skew tableau. If this C10 is the 8th smallest one, then you put it in the 8th tableau. So that's how you order the new pi. Am I making it clear? So that is how we do this, like the order of this like new pi. Right. So now, like, so that gives us like all the information that we need to compute the right-hand side. So I'm not ending my talk yet, but I just want to let you know, if you want to know more that like definitions and examples, you can actually go to my website and you have a bunch of stuff that you can see here. Okay, so let me just share another screen. All right, so this is actually my, so if you look at my website, I updated it. So you will have the Den and Nest and Warrington conjecture. And if you, the reason that I didn't go through every single thing is like, for example, if you just click on the detail of the Hecker algebra, you'll realize that there are lots of stuff here, right? And like, it's just too much to go through for three-hour lecture. But if you want to know like the Warrington Den, I have specific examples and then going through all these dens and nests for you. So if you're interested, you can actually go into my website and look at all the details here. So they are like really with all the details so that you can understand the proof. But for me, I'm not going to do that just for 3 hours. I realize that it's impossible. So for the next maybe 20 minutes or so, what I want to do is to give you like an idea of how to construct like the sure cat. Remember that we can actually have like a cat and animal and then all these dens and nests. So I want to actually give you an idea on how to do that. And to do so, I have to switch to my iPad. But I think this is kind of like a good time for you to, if you have any question, to ask me. So feel free to stop me like if you have any questions.
Yeah, Anna.
Mm-hmm.
In your formula that you just described in detail, you have the sum, and I'm curious if there is any cardinality for the dense summation.
Oh, so you're saying
how many
dens and nests are there?
Yeah, for a given lambda and MNN.
Given that, let's see. I think you can count it. I don't think we have a nice answer because like I do think that counting is not hard because you already have all the constraints. So it should not be too bad, but it is something that we haven't actually looked at, like how many of them. Yeah.
Thank you.
Just a very broad question. I'm trying to say this in the most polite way. How the heck did you come up with this?
Yeah, so that's why let's see. So like if I go back to my slide, so remember the SureCat. Let's see.
Yeah.
Let me just again. Share screen. All right, so so the proof here, so this is actually the whole thing. If I know, because I know this, okay, so I know the relation between the SureCat and this, right? And then so we just have our SureCat, and then the main theorem is to study the SureCat. So so this is our main theorem. I just need to know what is the polynomial part of our SureCat. So, and this guy is something that we discover when we are looking at LT polynomials. So we have a more generalized version for the polynomial part of LT polynomials. And because sure function is just a very special LT polynomial. So that's why we need to do that.
So you kind of knew the symmetric function side. You had intuition for what that ought to be, but of course, determining all of these statistics in the combinatorial side, I mean, is it something beyond a lot of experimentation, look at a lot of examples, or are you at a point where you can start to say, oh, we would predict it would be this, or?
Oh, so actually the proof in our shuffle theorem helps us a lot, because like all these things that you see, like, oh, we have to order things in a certain way, right?
Yeah.
And like when we prove, so it was like we experiment a lot, but like for the proof of the shuffle theorem is not as lambda. So each of the skew tableau becomes like a one row or like column tableau, one row tableau. In our notation is one row. So you have row tableaus, and then we know how to order them. So now we are just looking at like sure functions, right? So that just means that we are going to use the same thing, but now our row or column tableau are not just one row or one column. They are now like actual Young tableau, like sure functions, right? So that is like actually building up from our previous result. It's not like suddenly we magically know all these like area and diff and all these things, because like for sure function, like for shuffle theorem under any line, you only have one thick path below. Now you have nested one. So the only thing is like, okay, well, if I have nested one, how am I going to deal with the statistic when I have more paths? So usually a naive way is to just add things up. So if you know one, you know all, right? So that is how we come up with all these. It's actually based on the shuffle theorem under any line, and then we come up with that.
And then, of course, you also have the Loehr-Warrington conjecture when M and N are,
Yeah.
M is N plus one.
Yeah.
And then they have the right-hand side.
Actually, that is a very interesting thing, because their our version is actually quite different from their version. So it took us in my notes, it took us 17 pages to check that the two statistics actually are equal. And that's how we find out there's a typo in their publication. In the literature. Yeah.
But their LLT polynomials, aren't they the same set, or do they?
I think they are the same sets, like all the things, like just that the way that they define their labeled nested path is a little bit different from ours, and the way that they count the dim is also a little bit different from ours, because like they have a specific, like they're labeled a nested path. When they calculate the dim, we have to actually match our statistics. So the matching part is actually taking us the longest time to match theirs. So this is like our version. If you look at the original version, it's not the same. like this combinatorial side and the original Warrington combinatorial side are not the same. But they are both giving you a combinatorial side. So to prove the classical, like the classic way or the combinatoric formula that they have, we have a whole section to just match up all the statistics.
Oh, wow. Okay.
Yeah, so it's very different actually. Yeah. Any other questions? I don't see that in the chat. So yeah, I mean, today I actually have to fly back to Charlottesville. So I have a car to pick me up at 1:10. So I have to really be sharp ending the talk at 1. But I have time here. So let me just share screen and bear with me because my computer just updated and the Zoom just updated and I cannot find things most of the time. So bear with me for a little bit. All right. So what I want to actually do with you today is to like do some CAT example so that you have an idea. And also, if you want to know more, again, you can look at my notes on the website. So let's see. Share screen. Here. Hopefully, you can see my on the screen here. All right. So, so you may ask, okay, well, remember I'm telling you that, oh, you can always make your CAT, right? Like you can pick your RQ, RT, RQT, and then pick your favorite sequence, then you can make your own CAT. So, so what is going on with the main theorem that we have? So let me just really write down the theorem. So main theorem is not just for Warrington, it's not just for the sure CAT. Okay, so the main theorem is that I give you this given a then. So the H is the H that I taught you, the P is again the P that I said, and I have some D and E here. So the D is just the source, like the where the sources are and there where sinks are. Okay, so they are just the statistics for the Y coordinate of the source and the sink. And then I'm going to get a G. Let's just define it as the summing up all the distance between your source and the sink.
Anna, are you writing? Because I'm not seeing anything.
Oh, okay. That's
Or
weird.
I'm just seeing the very beginning and then it stopped. Is that
Oh, okay.
having that problem?
Let me, yeah, maybe I just share again. Let's see. AirPlay here.
Ah, now I can see it.
Okay. Thank you for letting me know.
Not a problem.
Because I don't actually know when I'm like.
No,
doing
you
this.
can't tell on your end.
Yeah, but if you stop again, let me know because Zoom just updated and then like everything is a mess. I couldn't even share screen before. So when I write this, can you see it now?
Yeah.
Great. Okay. So now I'm going to define our CAT. Okay. So define a cat and animal. Okay. H. So it's defined as this. So H, to define it, you have to have your Q root set, you have to have your T root set, you have your QT root set, and then you have your G the G's. So so let me just write it down. So D0 minus E1 up to D0 minus E1. Okay, so you're copying that many of them. So there are G1 of those things. Okay. And then you do the same thing. D1 minus E2. D1 minus E2. And that's the G2. So then gives you all these DI and EI, and that's going to help you to choose your sequence, the lambda. Okay. And then you do all these up to the last one, which is DH minus, I think it's DH minus 1 minus EH up to DH minus 1 minus EH. So that's a long thing, okay? And I'll help you to understand how we usually look at it. So you define this. So you pick your RQ, RT, RQT in such a way that first of all, like, so this guy, the length is just summing up all the G's, right? And then RQ and RT are equal. Okay, so you choose the same thing for Q reset and T reset, such that they are epsilon I minus epsilon J, where I is less than J, I, J are in distinct blocks of partitions. The partition L is just the sum of everything. So this has L number of it. So that's the L. Okay, into intervals of GK. And then RQT. Are just epsilon I minus epsilon J. So these are just positive roots. So we're saying that, okay, I'm going to choose positive root R, Q, and RT in RQ, which is actually the same as RT, such that I, J are in non-adjacent board. Non-adjacent blocks. Okay. All right. So I'm going to build up a cat like this. Then the H polynomial part of H, or in our way is the polynomial part X of H. Okay. That is given by pi in the nest, and then T of the area of pi, Q to the diff P of pi, that's all what we discussed it. And then the LLT polynomial mu pi.
I cannot see again if you're writing.
Oh, you cannot see the screen I'm writing again? Oh, I hate this.
It stopped again.
Okay, let me just share again. That's so strange. Stop mirroring and then mirror again. Okay, fine. Can you see it again? Like, if I write something, can you see that? Good.
Yep.
Okay. Luckily I didn't pay for Zoom. Anyway, so this is the conjecture, and that actually may help answering the question of Brandon, because he was like, oh, how did you come up with something like this? So this is like our main theorem. This is like the big thing that we discovered, that if you choose the right root sets and a way to construct all these like lambdas, then you can actually find a combinatorial interpretations of these cats when you truncate it in a very nice way using LT polynomials. Okay, so of course I'm not going to like talk about the proof, but I'm going to just give you an example and like how do you construct a cat and what does a cat look like? All right, so so like let's just pick something. So like and also in like I told you that we can construct the H and P in a certain way. And actually, in general, you can pick any H that you like, and you can pick any P that you like. You don't have to like have a constraint on your M and N. The constraint that we have is just like for Warrington. In general, this works for any H, any P that you choose as long as your P is not like irrational. So let me just give you an example, okay? So say, for example, our H is 3, our P is 1 plus epsilon. Again, if my screen sharing suddenly stops, please let me know. Okay. And then so now I'm going to draw this guy. So and then so 1, 2, 3. I'm going to give you some source and some sink. So I choose my D as my sources is 4, 2, 1, -1. And my sink say is 2, 2, 1, 1. Okay. So in our, this is just something that I picked here, but in general, if it is low Warrington conjecture, we have a way to construct them, just as what we said before in the first half hour. Okay, so from here, you can easily compute the G, right? So the G is just the, to just recap, the G is this guy, okay? So it's just DJ minus IJ for each of them. So here, my G is just 4 minus 2, right? So yes, 2. Okay, so and then the next thing is that you add them up. So the next one is 4 minus 2, which is our 2, plus 2 minus 2, so 2 plus 0.
I get stopped again.
I hate this. Okay, let me just do it once more. If it stops, then I give up. All right, no, sure. All right, so can you see that? Okay, so again, I choose H is 3, choose my P, which is 1 plus epsilon, so that it is non-rational, so irrational. And then now I'm going to compute the G. So what is the G when you have the source and the sink, okay? So the 4, 2, 1 minus 1, 2, 2, 1, 1. So the first one is 2 is because I have 4 minus 2, that's it. This one is from the first one that you have plus 2 minus 2, so 2 plus 0. So I still have a 2, right? So this guy is 2. And then the third one is the previous one plus 1 minus 1. So again, it's plus 0. So you have 2, 2, 2. Okay, so that's the G. So the G is just helping us to know the block that you are going to draw. Okay, so if you're wondering what are these like D and like different things here. Oops. Okay, so this D here 4 is just like 1, 2, 3, 4. So this is our 4, and then my sink is just like the 2 here. Okay, like those. So that's the 2, and then 2 and 2. Okay, and then 1 and I'm so sorry about this. This is like terrible interface. And then minus 1 and 1. Okay, so these are the source and the sink. But it is not going to help you to understand the mechanical, the cation animal. So let me just draw the cation animal for you. So how do you choose your root sets, right? Like what are these? So usually what we do is that, okay, we have this 2, 2, 2 here, right? So we are going to have a length, which is just adding all these 2's together. So our length here would be 6, okay? So what you do is just to draw this out, okay? 1, 2, and then 3, 4, 5, 6, so duplicate. So why do I draw something like this? Is because on this side here, right, they are positive roots, okay? So if you look at so that's usually how we work when we actually do our research, is just drawing something like a staircase. And then how are you going to find your RQT root? Because of the 2, 2, 2, it's actually giving you a block, okay? So the block here is just, okay, the Q, because the first one is 2, you draw a block like this, all right? And the second one is 2, so you draw a block like this. The third one is 2, so you draw a block like this. Then your RQ and RT are just these positive roots. Can you see what I wrote? And then, so that's the RQ and RT. That clear? And then now, what is your RQT root? So RQT root is very easy. So when you have these two blocks, draw a bigger block. Okay, draw a bigger block here and draw a bigger block here. Whatever is left here, this is your RQT. So you have this R, so that just means that, like, if you want to really draw out the roots here, then, for example, where's RQT? RQT contains 4 things. So 1, 2, 1, 3, 1, 4, 1, 5, and 1, 6. So you have 1, 5, 1, 6, which is the root thing. So this is just epsilon 1 minus epsilon 5. This is epsilon 1 minus epsilon 6. And then you have 2, 5, and 2, 6. So this means epsilon 2 minus epsilon 5. This means epsilon 2 minus epsilon 6. So these are the root set that you have. Okay, so that's the RQT. And then you have RQ and RT. So that helps you to build up this guy. Now you just need to know what are the like the numbers here, right? So usually when we write the number, we write on these guys. So a cat is always like, you know how you choose your root set, and then you write the numbers. So how do we write the numbers? Like, what are these guys? So D0 minus E1, D0 minus E1 is 4 minus 2, which is 2. So you have 2 2's, 2 and 2, because I want G1 that many of them. And then D1 minus E2 is just 2 minus, I think D1 minus E2 is 2 minus 1, because we start with 0. So that's 1. So that's why I have 2 1's here. And then D2 minus E3 is just 1 minus 1 is 0. So you have 0, 0. Okay, so that's that. So this guy is our cat. Okay, so this is our cat. We form the cat. And then, so what is it in algebraically, right? So algebraically, it is just like summation of omega in S6, because your length is 6. And then you have your omega. And then our, like, you're using C1. So how many C1 are there? So we have C1 squared, C2 squared, C3, and C4. Okay, so why is that? Because you have 2 1's, 2 2's, 1 3, and 1 4, no 5, no 6. So that is what it is for the Z to the power lambda. And then now you have this 1 minus QT of what? So C1 over C5 1 minus QT C1 over C6. How do I get this number? Is these numbers, you see? And then 1 minus QT C2 over Z5, 1 minus QT Z2 over Z6. Okay, so that's our numerator. Okay, and then what are the denominator? Denominator here is 1 minus, without Q and T, is Cj minus Ci, where I is less than J. Okay, from 1 to 8. From 1 to 6, sorry. Yeah. And then what are our QT? Well, the QT are all the IJs in RQ and RT. And then you have 1 minus Q Ci over Cj, 1 minus T Ci over Cj. Okay, and that is the whole cat. And then so that is our cat here. So this is what cat and animal is. So this guy, again, if you do, if you really write out, it's a series of terms, and then you truncate it such that it is just only with the the sure functions terms, and then that would give you a LT interpretation. So this is our H that we have there. So our H there. And then you take the polynomial part, then we know that you can write in terms of the LT. So what it means to our Loehr-Warrington is that Loehr-Warrington gives us a way to construct our H, our P, our D, and the E, so that you don't have any freedom. And then, but with this statistics, you can create your cat, and then you can use this formula so that you know the combinatorial interpretations of all these cats. So Loehr-Warrington cats are actually a special cat. We have LOT cats. So we have other types of cats. So that's the idea. So just to give you just this idea is that if you have like your statistics, HMP and sync and sources, you can create your own cat. So this is what I want to share with you today. Sorry for all these technical things happening.
It's 1:02. I guess Anna's got to get going.
Oh, it's fine. You can ask a little bit
Okay.
question. The
Do
card
we have a
comes at 1:10.
Any questions? All right. Well, let's thank Anna. And next week, Anna has one more talk, and then Brendan is starting a 2-talk series.
Yep.
So we'll see you all on Tuesday. Have a great weekend. So.
Have a great weekend, everyone. Bye.